Okay, so today we're going to have a talk by Mei Rose Connor, and the title of the talk is From True and False to JSL, an Adventure in Logic.
Thank you very much. I'm going to be doing this partially from my, I have from about 3/4 from my chalkboard and 1/4 from my computer. So just know that. This talk is dedicated to John Horton Conway. Maybe we all remember him well. So we're going to go on an adventure tonight, but I thought that a good place to start would be in two-valued logic, which is what most mathematicians are used to. It has two what are called truth values, and they are usually called true and false, though I guess the computer science folks would call them 1 and 0, but we can define certain functions called truth functions, which take either 1 or 2 of true and false, and output a third truth value. And these are called the logical connectives, and there are 5 fundamental ones, and they are written like this. And this one is called not. This one is called and, or, and a special note that this is the inclusive or. There is a way to handle the exclusive or in terms of these other connectives. So when we say or, we can say A or B. We also mean that it can be A and B. We have a material implication, which is usually written as if the first thing, then the second thing. And we have the biconditional, which is usually stated as if IFF or are we still visible?
Yes.
If and only if. So these each have, all of these except for not take 2 truth values and output a third.
Just a quick comment. Can you maybe move that chair?
Yeah.
Thank you.
We can go through these, what are called truth tables, to explore the relationship between all of these very quickly. So if we have one truth value and call it P, and we want to find not P, if we have true here, the not takes only 1 truth value. It's unlike the other ones. We can take the opposite of it to get not P, which I suppose makes some sense. And the opposite is also true. So whenever we have a statement that has a truth value, you can call it P, that's either true or false, we get the opposite, the other truth value when we take its negation. And or, and the other two take two truth values, which we can call P and Q. So we can first define P and Q. P and Q is only true when both of the parts going into it are true. Otherwise, it's false. It gives an output of false, the truth function. These are the four possibilities for the inputs with P and Q. Each can be either true or false. So these are all the possible combinations, but only one of them gives us true when we join the two statements with and. We can contrast this with or, which is written like this. If we remember that this is the inclusive or, we consider it to be true when at least one of the parts of it are true. So this comes out like this. In this case, we do not have at least one input that's true, so the output is false. We see this duality with and that we'll state later as an important theorem. I'm sorry I have to erase so much. It's just a consequence of this chalkboard being little. The implication, if P, then Q, which is written like that, behaves a little bit differently from the other two in that it's asymmetrical. If we put in the possibilities here, it is only false in the case that Q is false and P is true. Otherwise, it's true, and we can argue about this from a philosophical standpoint or a standpoint of looking at what would happen if we took P does not imply Q, or if P then not Q, and then took the negation of that, if that makes any sense. Another way of saying this is that we can derive anything from false assumptions. So if P is false, then no matter what truth value Q takes, the statement, if P then Q, will always be true. The statement, P, if and only if Q, can be thought of as saying, if P, then Q, and if Q, then P. So if we analyze it that way, we find that it's only true in the cases where P and Q have the same truth value, and it's false otherwise because one of the directions of implication wouldn't work. And then our and would be false because not both of the parts of it would be true. We have a notion of proving things using connectives where we can build up statements to prove using fairly simple rules. If we have P, Q out to Z are called well-formed formulas. And then the following are also well-formed formulas. And I will use the Greek letters to represent the fact that we can put well-formed formulas inside other ones. We can have the negation of any well-formed formula, not phi. We can have the and of two well-formed formulas. We can have it with or, where
We have a question.
a question.
Oh yeah, so it's like what are our basic like well-formed formulas? Like what are like base?
These are P through Z. This is taken
okay.
from K and M.
Okay, so you're saying that we're starting with those. Okay, cool.
We can also make more of them using subscripts.
Sure.
If you need them, please. We're not going to do anything that complicated. But if you want. So from these, we can get to any of these, and which then can be, these are all well-formed formulas. So therefore, they can be put into these schema also. And another rule is that nothing else besides this is a well-formed formula. So with those rules, we also get a set of inference rules which allow us to take statements and well-formed formulas and turn them into other well-formed formulas. And this is, I'll give some examples of them. If we have a well-formed formula phi, then immediately from this we can get not phi. This is called double negation, which makes a little bit of sense if you think about it in terms of language. This is a rule that tells us if we have any well-formed formula, we can add 2 not signs in front of it and still have a valid well-formed formula. We have some rules that may be familiar if you've studied argumentation in the formal philosophical sense. If we have if phi, then psi, where phi and psi are well-formed formulas, and we have phi, then we can get psi. This is called modus ponens. These are 2 examples of inference rules that allow us to take well-formed formulas and create some new formula out of them. These are what allow us to move to write proofs in formal logic systems. Well, natural deduction formal logic systems. We can prove in this logical system, we consider a theorem to be a statement that has no assumptions in it. For example, some rules for going from one well-formed formula to another are considered theorems. For example, we noted before that the duality exists between and or. Another way we can express this is that if we have the negation of an and statement, it will have the same truth values as the negation of both parts with or instead of and. This is a theorem that we can prove. It has no assumptions, and it will always be true no matter what the values of the statements phi and psi take. Would anyone like to see this proved? Or should we go to the next section?
I don't think we really define like what a proof is though. Like I don't think we know what a proof is.
A proof is in this system that we're working in, a conclusion that may or may not come with some assumption, some premises. This statement does not come with premises, where we can move from using the inference rules line by line to or if there is no premises, then to derive the conclusion as true using inference rules. Is that okay?
I guess, sure.
Again, I can prove this statement to show an example of one possible layout for a proof, or we can move to the next section if everyone's okay.
So would it take too long to show the proof?
It's a little bit long.
Then never mind. You can move on.
Okay.
You could always do it at the end if we have extra time or if people want to see it.
Okay. So the next step that we can take in logic that comes from people's natural wonderings about how logic should work is, should logic include the realm of the possible? Things that are possibly true, that they are not always true, but they are possibly true. Or things that are true at some point in time, but not true later. We can contrast these with the things that are always true, or the things that are necessarily true. So to do that, we introduce two new logical symbols, the box and the diamond. The box before a statement means that it is necessarily true, or there are many interpretations of this, that it is always true, that it must be true, and so on, as well as, and the diamond represents things that are possibly true, or sometimes true. We have also methods for building up well-formed formulas from these statements. And they are the following. I'll put all of them because there aren't that many. We consider these to be axioms. If something is necessarily true, then it is possibly true. This makes sense. Because of our definitions of necessarily and possibly, that things that are possibly true, well, the things that are necessarily true are always true. The things that are possibly true are sometimes true. So if it's always true, then it's definitely sometimes true. If something is necessarily true, then it's true. This is fundamentally kind of a tautology that I guess we could argue about what it means philosophically, but I'm not going to do that. If something is true, then it is necessarily possibly true. If something is necessarily true, then it is necessary that it is necessarily true. This is similar to this one, but different in that we have, if it is possibly true, then it is necessarily possibly true. We still see?
Yes.
And finally, this axiom if it is necessary, that if it is necessarily true, then it is true, then it is necessarily true. These are the axioms that allow us to build well-formed formulas using these two symbols. There are also some inference rules, but we're not going to discuss those so much because we would like to move on to the next part of the talk, which is the latest result in 7-valued logic. And I'm now going to move to my slideshow presentation on the computer. So, JainaSyadLogic, I apologize for my pronunciation of the Sanskrit. I have not found a reliable pronunciation guide for from transliterated Sanskrit to IPA, so that's my approximate pronunciation. Comes from an exploration that I was doing one day on Wikipedia. I went down a crazy Wikipedia rabbit hole learning about the Jain system of metaphysics and how the Jain religion derives metaphysical truth, which is through this system, through a system with 7 values of truth rather than just 2, which was what we were doing before, true and false. So there's this is the motivation for the 7-valued logic system. Anekantavada is the idea that there are no absolute truths in the universe. I am not going to argue whether this is true or false, but it's important to note that this is a fundamental tenet of the Jain religion. It also comes with kind of a corollary called Syadvada, which means that there are different shades of truth and falsehood to every statement. That statements can be a blend of true and false at the same time, and that this does not conflict with the nature of the universe. This means that all things are in this state of change at all times, particularly the universe and the gods. So the Jain have developed a system called Saptabhangi, which means the 7-fold predication. In other words, 7 different values of truth. And because of Anekantavada and Syadvada, statements can take on multiple of these truth values at once. And in this column, I give one possible translation that I found of these 7 truth values from the original Sanskrit. The key word in the Sanskrit I learned is syad, which is where the name of the logic system comes from. It means possibly, or it may be. I found more than 20 different translations for this word in a Sanskrit dictionary, and they all seem to allude to this sense that something may or may not be actually the case, it is possible that it is the case. So we just went through these, but we have to introduce one more symbol before we can understand my work on the 7 values of logic. Notably this symbol here, which means that it is provable that the statement P is true. So this is a little bit of an info dump slide, but this is how I have chosen to represent each of these 7 truth values where we have true and false, but represented in terms of modal logic statements about a statement P. The interesting thing to note is that when we have the combinations of truth values, we have to use or between them to avoid paradoxes. But all of this is stated within the realm of the possible. An interesting thing that arose when I was working on this at Math Club was that these truth values correspond to a nice lattice if we allow for a null truth value, which we could have a philosophical interpretation that is still open. But because this structure resembles the power set, the Hesse diagram for a set with 3 elements, we thought that this could have some implications for the relationships between the truth values. Finally, we have a further outlook into and we would like to look into this further, pushing into theorems and tautologies with this system. We still have not yet established what it means to take the fundamental truth functions on these truth values, given that the truth table would be 128 rows long, if I did 2 to the 7th power correctly. This needs to be analyzed in a much different way than the true and false, the bivalent truth system that we're used to. Once we have those, we can begin to develop inference rules for them, and then look into proving theorems about the relationship between these 7 values, and in some kind of natural deduction system, such as K&N. And a fun side note about this project is that my mentor on this project, Professor Marr, said that he was reminded of Raymond Smolian's hardest logic puzzle ever when I introduced these 7 truth values to him, and suggested that we make the hardest JSL puzzle ever with 7 divinities instead of the 3 from the hardest logic puzzle ever. That's still in progress, and I hope to present that puzzle at a conference in April. That's the end of what I have planned. Any questions? Julian?
I wasn't raising my hand, but
Oh.
also I guess you could, if you want to, you could show that the proof that you mentioned earlier.
Sure. Okay, so I'm going to carry out this proof in the K&N natural deduction system. And there's some inference rules that are in it that I will explain when we get to them. So we begin the proof by stating the conclusion we wish to show. Because this is a biconditional, which means we want to show that these two things have the same truth values for all instances of P and Q. We need to show first the if direction, and then we will show the only if direction. This may be familiar to people used to writing regular proofs in mathematics. So we say that we want to show the one direction one thing that we can do when we have a conditional, we want to show a conditional, is we can assume the first part of it in order to show this second part. So we can begin the proof, number the lines, put in this statement, and we get this from an assumption for conditional derivation. This basically means that we're trying to prove a conditional, so we're going to assume we get to assume the first part. And if we can show that the second part follows, we'll have successfully proved the conditional. We write in that we want to show the second part of this conditional. And when we do that, maybe one proof method that you're used to in the rest of mathematics is proof by contradiction. So we can assume that this statement is not true. So we put the not in front of it, and we get to assume that because we're carrying out an indirect derivation or an indirect proof of this statement. Something that we're going to use that we have proved before, but not today, is that this statement is equivalent to that, which is essentially the dual of what we're trying to prove. But we can, because it's a separate theorem, we can say that we can use it in this proof. Is that okay? It's called De Morgan's law, and we, in the K&M system, we write the line number that of the line we used and the inference rule we used to derive something new from it. Now, an inference rule that is sometimes forgotten when inference rules are listed, but very important, is the fact that we can repeat statements that we already had. So if we have a statement phi, then later in the proof we can also use that statement phi. So we have up here the negation of P and Q. To repetition. We used 2 and we repeated it to get line 6. Now, we have arrived at a contradiction here. We cannot have both of these statements be true at the same time. So by the usual principle of proof by contradiction, that means our assumption was false and our theorem is true. So this part is true, and we write the lines where the contradiction appears, and indirect derivation, or proof by contradiction, in other words. The K&M proof method says that when we finish a subproof, we put it in a box and cross out the word show to represent the fact that we can now use this line in the rest of the proof. Since we've shown the second part of this conditional here, we've solved that part of the proof, so we can put that in a box. And we have, oh, I went too far. Three, and we arrived at it by conditional derivation, which is the one where we assume that the first part of the conditional is true and derive the second part. We successfully derived the second part of the conditional, so which is here. So we get to consider that part of the proof finished. This is half of the proof because we have a biconditional and we've only shown one direction of that biconditional. The rest of the proof is similar. And once we arrive at the second part of the conditional, we use an inference rule called conditional to biconditional, where if we have two conditionals, one which says if phi then psi, and the other says if psi then phi, then we can get a biconditional between them.
Thank you.
That's all I have prepared.
Any further questions?
So, seeing how your system is 7-state logic instead of 2-state, I'm wondering how unmanageable it gets to table cases into truth tables, because instead of 2 to the n, you have 7 to the n. How do you deal with that?
I haven't dealt with it yet, is the truth. I've been thinking a lot about how to do it, and I think I'm going to have to do it similar to the way that Claney developed the 3-value truth system, which is to take we want the true and false to behave the way true and false do in the normal 2-state logic system, and then try to base everything else around that to preserve relationships like the duality of and or.
Okay.
Does that like cut the time down?
What?
Does that like somehow cut the time down it takes to like check if something is true? Like doing that?
I would think so.
I know that electrical engineering and circuitry uses, they actually apply a 3-state logic system where there's 3 states, there's true, false, and unknown. I see that your 7-state logic system has true, false, unknown, but then it has 4 other permutations of that. Why did you choose to do that?
Well, the 7 states are taken directly from sacred Jain literature on the Saptabhangi, the 7-stated predication. So that was my real inspiration for this project. Those are the 7 states which the Jain philosophy allows, and I wanted to see if it was possible to create a logical system around that.
And just getting your opinion on this, could you use, then theoretically, probability as a logic system? Like an infinite state logic system?
Yes, there are such things as infinite state logic systems, and I know people who work with them, and I have tried to work with complex valued logic systems with little success.
That sounds horrible.
Say, I have a question.
Yeah.
Did the Jains create their own, sort of make their own proofs, or did they just sort of assert the Anekantavada and just sort of leave it at that?
I have tried to read analysis of the Anekantavada. It's very metaphysicsy and not very much logic. Like they say things like, well, like the truth of the statement, the pot has water in it, depends on can be true or false depending on who's looking at the pot or what time of day it is. So therefore, this system must be true. And if you look at it like from the metaphysics standpoint, I think it looks pretty flim-flammy, but from the logic standpoint, I think that this system can actually prove some stuff that they weren't expecting to be able to be proved with this.
I don't know if it's possible, but if you want to, I know you made like a automatic proof system for 7-state logic systems. You want to show that?
It's not the 7-state logic system. It's regular 2-valued logic. It's just set in a different deduction system than the one I proved this theorem in.
Oh, that's still really cool.
Does anybody want to see the proof engine that I wrote?
Yeah, that'd be cool.
Yes.
So I built this thing at my work. I'll turn the tutorial on so you can see it. This is drag logic. It's actually inspired by the Logic 2010 proof software that we use in the philosophy classes at Stony Brook for logic. And my boss and I had this shared vision of making a better version of that software that has less eye-melty colors and better drag and drop support. Because we had to really simplify things, we chose the Lukasiewicz axioms of logic, where we take only three axioms for moving from one well-formed formula to another, and that rule that I mentioned called modus ponens, as well as substitution. This is compared with, if you compare this with the K&M logic system, which has many more axioms and at least 7 inference rules, this is really, I mean, you can prove that it's the minimum number of inference rules and axioms that you can have and still derive all of sentential logic. So the proof is here. The statement that you want to show is at the top. The axioms are in the middle, and then I'll show how this tool works. You can use this tool to create new well-formed formulas. The only 2 kinds you get in this system are the negation and the conditional. And these are the letters that are available for you. I have not yet developed any proofs in this system that require more than that. This is the modus ponens maker. It takes if phi then psi in the top box, phi in the bottom, and it will output to the proof psi. And that's the one for the Tor. So we can drag letters onto here to produce new well-formed formulas. If I want to demonstrate how the modus ponens box works, I'm not moving anywhere towards proving this statement, but I can put this in here. I am shown the second part of the conditional, which is the first part of the conditional, which is expecting. I have that right here. I can plop it in there, and it will output the second part of the conditional by modus ponens. The goal with this tool is to prove theorems, because we don't yet have a tool for adding premises. And it does have a PHP support for saving proofs on the server after they're completed. You just can't access them, but I can. There's also a nice surprise for the user if the proof gets completed. This is Peirce's law, and I have not proved it yet in this system because I have not proved it in the K&M system. So I imagine that it is much, much more difficult to prove in this system. This would be fun to have in 7 values. I don't know how that would work quite yet, but that's another logic related thing that I've worked on.
Can't wait until automatic complex valued logic systems.
Why could those shouldn't be able to exist though?
Yeah, I don't exactly know how you talk about imaginary probability.
I mean, like the harder problem is really the fact that there's a lot more values. Like it's not a finite number of values. Like it's
I mean, you could just
go on.
You could just talk about it like probability. I mean, it's basically the same thing because P naught is 1 minus P. So like negation could basically just work the same way, and works the same way, stuff like that. But it's an extension.
If you take bitwise and or bitwise or on the continuum, you can get really cool structures. Instead of truth tables, you get truth solids. And if you give me 1 second, I will run and get my 3D printed model of the truth solid for and.
Yes.
Do you want to see that?
Yes.
We want to see the truth solid.
Well, basically a bunch of 3D Sierpinski triangles.
Yeah. That's the weird thing. And or is the dual of this, but I haven't 3D printed that yet.
Hey, this might relate to cellular automata, which is what I'm going to be talk about.
Yeah, actually the person who developed these truth solids is my boss, and his coworker Patrick Grimm has a website where you can explore these solids, and he also talks about how to generate them with cellular automata, which was actually what my boss did first, was stepping through the layers of the truth table for bitwise and bitwise or at the different levels as cellular automata. And then finally, they realized that if you stacked them on top of each other, you could get a solid, and they made this thing.
Your boss wouldn't happen to be Stephen Wolfram, would he?
No.
Because that sounds so similar to like completely different field, but the base.
I'm gonna post the link in the
Also, we should probably wrap up this.
Sure.
So if there's any like last things people want to say before we end the recording, do that now.
0 is not a part of the naturals.
You are wrong, but okay.